9:30, so we're going to go ahead and allow Christian to start.
All right, everybody, you've made it to the last session. Lunch is almost here. So my name is Christian Sorensen, and I'm genuinely excited to tell you about space weather today. So let's get started. First of all, I'm going to provide a little bit of background on what space weather even is, why we should study it, why we should care about it. Then I'm going to talk about how we detect what's known as these ultra-low frequency waves. We'll get into what those are, why they're important. And then I'm going to tell you about my role in this process, which is developing a software tool to analyze data in the effort to find these ULF waves. So all of you have heard of the sun, right? And the sun is constantly throwing out particles and energy and radiation, and it creates what's called the solar wind. And the solar wind hits our atmosphere, and normally it could burn the atmosphere. It would be very dangerous. Places like Mars that don't have an atmosphere, the surface is constantly bombarded. But we are lucky enough to have the magnetosphere. The Earth acts like a giant, magnet, and this huge bubble of magnetic energy protects us, and it deflects all of these things. But when the solar wind is energetic enough, it can impact that magnetosphere, and it causes these large waves, almost like these ripples, to propagate down the magnetic field lines. You can see some of these lines and how they kind of collect at the north and south poles, just like a bar magnet. We've seen those images, and so we're going to try and find those waves because they can be kind of dangerous at times. When a ULF wave hits the upper atmosphere, known as the ionosphere, it can cause what are called scintillations. And these are basically disturbances in signals that we might be sending up through the atmosphere, whether it be communications, GPS, your Instagram photos, anything like that. And it's those disruptions can be bad. They can tell you that your plane isn't where it is, that your satellite isn't where it is, that light didn't actually come through from your best friend. But so it's really important that we know how our atmosphere is being affected by the solar wind, by these large waves, and ultimately what this is really about is building a better understanding of our local space weather environment. Just like it's important to understand how the weather affects us here on Earth, it's important to understand that on a much larger scale, especially as humanity pushes farther out into space. So this is a personal analogy of mine, and looking up through the ionosphere as we do with our GPS receivers and things like that, and look at these signals, it's kind of like trying to understand how light is distorted as if you were to look up through water. So you're underwater, looking up, you'll see the image kind of distorted, and that the surface of the water could be disturbed by wind here in the atmosphere, and similarly our upper atmosphere is disturbed by the solar wind, and it causes these fluctuations in the ionosphere. And so that's kind of what we're trying to do. And hopefully we can eventually build a model to understand how the wind is affecting that surface, how these ripples are coming across, and how we can better understand them and better protect ourselves from their negative effects. To do this, we put a bunch of sensors in the ice. Well, not me, but the MIST team, as part of the Space Department at BT, since 2011, they have been putting these sensors in the ice all across Antarctica. And what they do is they have dual band GPS receivers, which monitor GPS signals that pass through the ionosphere. And they also have magnetometers, which measure the fluctuations in the magnetic field, and those are at the Earth's surface. By comparing these two signals, we can learn a lot about these waves that might be passing through the atmosphere. These stations are located in Antarctica, like I said. They're aligned with the 40-degree magnetic meridian. As you might know, the magnetic poles are slightly off-center from the geographic poles, and so when we're studying things with their magnetic field and these magnetic field lines, it's important that we are aligning our stations with those in order to get the best image that we can. Seen here in red, these are the current stations. There are 6 stations. There are plans to include more, and this also highlights what's unique about this work. While the concept of using these GPS technology to detect ULF waves was proven a few years ago, this is the first team to utilize more than one monitoring station at a time. And this allows us to get a better picture of what's going on. We can even see the waves propagate along from one station to another. And again, just building a better picture of what's going on. So the reason they're at the poles is, again, if you think of that picture of a bar magnet, you know, the north and south poles of a magnet are where all of those magnetic field lines, you know, come together. And so by placing sensors there, we get kind of the highest resolution, or, you know, the most bang for your buck for putting all those sensors there. That's where all of the activity, you know, kind of ends up happening. And when the solar wind will impact our magnetosphere, those ULF waves, those ultra low frequency waves, will propagate down these magnetic field lines, and then we can detect them with our magnetometers. So something you might know about, you know, that solar wind hitting our magnetosphere and it'll excite particles in the atmosphere, and we get this beautiful aurora. This is aurora seen from the ISS, and similar to what kind of like waves in the water. Again, there are sometimes these little eddies. You know, there's not these perfect symmetrical lines. You know, it's I don't know, it's nature. It's messy, but it can be beautiful as well. Another just can't resist putting more pictures of the beautiful aurora. This is also in Antarctica. Again, you're going to see those aurora, those activities near the pole, because that's where all this energy is being directed. Again, that's why we have our sensors there. And finally, I love this picture because you can see the ring of this aurora. And after seeing those graphs of the magnetic field lines, this does a great job of illustrating, you know, just how that energy is all focused in this region. Okay, my part. Like I said, my role in this was developing a software tool to help visualize and process a lot of this data. Like I said, the team has had these sensors in Antarctica since 2011. They've been collecting data for years. They have this huge library, and they needed a tool to be able to go through it. You know, what good is data if you can't process it, if you can't see what you got? So when I arrived at the team, they had a program that was built to look at a specific day at a specific time, and my role was to automate this program so that they could query their huge library of data with a certain date, input a parameter here and there for how they wanted that data to be processed, and it would automatically go through, determine what systems are available, what satellites are available, what time windows is that data being collected, and spit out a useful graph. So if I wanted to get into the code, I could show you something like this, talk about the sorting algorithms, but that could get messy really, really quick. Instead, I'll just show you, this is essentially what it does. Like I said, you input a few parameters, the data it's found in the library, it's imported, it determines, you know, what's what. It does some of our computing where we process the carrier phase. Again, this TEC. TEC means the total electron content of the ionosphere. Essentially, the ionosphere has a bunch of, you know, electrons floating in. The total electron content is how many electrons are in a given volume, and we can study how that amount varies in these fluctuations. If you imagine, like, again, even in water, or just, you know, a tank full of evenly distributed particles, and a wave propagates through, you'll see those particles squeeze together and spread apart. And so by measuring those fluctuations, we can detect those waves passing through. Some other statistical things are done, like we detrend, we apply, you know, high pass filters just to clean up the data, make it look as good as we can, and eventually it gets to a point where humans can do what they do best, which is notice things. And once all that is done, it'll spit out a plot with everything labeled, and we get something like this. Okay, so here in blue, these are those fluctuations in the total electron content. We can see them oscillating up and down. And in orange, we have, this is data from the magnetometers. And the reason that we use both is because sometimes the magnetic field is oscillated for one reason or another. Sometimes the total electron content might change. But when both of those change, it's a very strong indicator that some event has happened, that some big wave has come through and disturbed both of those at the same time. And that's when the team of scientists, and again, it's a pretty good team, can look at graphs like this, notice when there's these overlapping portions on the graphs, and say, okay, something must have happened there, and they can continue on their search. So again, my role is really just to build a tool to help them go through their data, help them notice things better, and continue this effort to better understand our local space environment. And yeah. Of course, got to acknowledge the Space at BT department. Super cool to work somewhere just for space in the title. Gotta love it. MAOP, the research program that's funded as National Science Foundation, which funds them, and this Virginia Tech scholarship I've been fortunate enough to be a part of for the past few years, which helped open the doors to be here. course, special thanks to Dr. Wayne Scales, who's here in the front, and Philip, a PhD student who's helping out all summer, especially being patient while I learned all this MATLAB code. I can't thank you guys enough. And thank you. Any questions? Choose first.
So this is really interesting, and so basically this data is building kind of a story why we should care, about these things happening. I guess what could we do about these changes? How could this information potentially be used? Because these the stuff coming from the sun can be dangerous, and well, I guess maybe a different question would be is there changes over time? Is there progression, of these disruptions?
Well, as you may know, the sun goes through an 11-year cycle where it gets more active and becomes less active. We'll see more sunspots, more solar flares, and things like that. And just trying to build a better model of how we can maybe predict that, similar to having a farmer's almanac, where we have a general understanding of what's going to happen and when. And then when things do happen, we can know how to maybe adjust for them. And I think one of the goals for understanding and having a very good model of how our upper atmosphere is being disturbed is maybe to either correct for things that might happen bad, or just ultimately improve the accuracy of signals that can come through the atmosphere, like GPS especially. Right now we have fidelity of about 10 meters, plus or minus 10 meters to know where a satellite might be. But eventually, if we can kind of perfect this technology, then we could get that accuracy down to centimeters, which then you can have things rendezvous automatically, and just it's pretty cool.
Okay, so that could be the most tangible application, is just improving the accuracy of satellite GPS.
That, and also like you said, the solar wind, it can be dangerous at times. And an important reason to understand our local space weather environment is occasionally you get a really big storm. And when a solar storm is big enough, it can dramatically affect satellites in space. It can knock out communications. It can ruin electronics. And so the better we can understand it, the better we can protect ourselves against bad events like that.
Something to the.
Oh, please, this is Dr. Staples.
Yeah, so that's an excellent question. I think the big picture here is, as Chris has articulated very well, it's a predictive capability. Just like we have in the lower atmosphere, we get up and see the weather, rain, sleet, snow. We can predict when a storm is coming. The space environment, the physics and chemistry are much more complicated than the lower atmosphere, and we deal with bigger spatial scales because we're looking directly at the impact of the sun on the earth. And at this point, we don't have computers big enough to do that. So maybe we're hoping within 20 years, computers will be big enough, and then the models will be sophisticated enough that we can do the same type of prediction out in space. If we know there's a storm coming, you can move your satellite. They're $500 million satellites. Instead of getting it destroyed, you can move the orbit. Astronauts would stay inside of some type of vehicle, won't be hurt or killed. So it's very similar to what we're trying to do in the lower atmosphere, but it's a more complicated problem, probably one more generation before we actually can get there. So.
Interesting.
Well, my question was somewhat silly. Several years ago, I saw the Northern Lights quite distinctly. I was amazed. It was incredible seeing it in Blacksburg. So, did you see that in those data?
Well, actually, our data doesn't really look for or at Aurora. I just like to use Aurora as an example of how that solar wind, is hitting our atmosphere, where it is, and it's exciting the atmosphere in a different kind of way. But again,
So it doesn't create the aurora necessarily.
Well, I guess it kind of does both. I'm sure if there's a very powerful solar event, I'm sure we get some combination of the two. But the aurora isn't. I guess that's not the dangerous part. That's just the beautiful part.
Yeah.
Yeah. And one more thing to add on what Dr. Scales was saying, yes, we're trying to predict and understand our local environment better. But personally, I also like to think even farther, in that the better we can understand our local space weather environment, the better we can apply this thinking and this technology to eventually understanding, the weather on the gas giants or on other planets, or, like the space race is on. We're going so many exciting places, and this is just, one more way that we can arm ourselves to learn more, to discover more, and it just doesn't get better than that.
Just at one point about the space, you said you saw the aurora at a very low latitude. We also are addressing that within our group as well. We've built a chain of space weather radars across the continental U.S. in Virginia and Kansas and Oregon, and those radars can actually sense impact of aurora, or if the storm gets to a mid-latitude where we are. So we're addressing that as well, but we're using different types of instruments to study that.
Okay. You had a question?
Yeah, I was curious as to whether your music background helped you understand these wave functions, or if they're just totally separate, if there was any advantage from that background.
So, some of you might not know, I also have a bachelor's degree in guitar performance, so I'm a professionally trained musician as well, and I've spent a lot of time in recording studios and thinking about waves of a very different kind, in audio waves. And actually, very early on, Philip and I were discussing an interesting way that you could look for these is you could translate these waves almost into audio waveforms. And when you're listening to audio, especially like in recording something you want to get rid of, is what's called phasing. Is when two signals are very close together but not quite on top of each other, and they'll start canceling each other out. But if you're listening to a signal where phasing is coming in and out, it's very clear when the phasing has gone away, because the sound will be very clear. It'll have the highest range of both low and high. And so if you could process some data like this into audio waveforms, I do believe that you actually could listen to it and you'd be able to hear when it changes from when it goes into phase and out of phase. And you could even use some kind of like Fourier transform or other things that would actually produce some pretty clear indicators, especially because our ears are very sensitive. And again, what humans are great at is noticing things. And so the more ways that you could process and use our senses to interpret the data and kind of make our ears perk up and say, hey, that looks like something, let's investigate it further. So it would be pretty cool.
Are people using data sonification for this?
I'm sorry?
Data sonification instead of visualization? Are people using that in this area?
Actually, I don't know. Have people tried to turn this stuff into sound and use that
Yes,
in another way?
actually the work that I'm doing in another area that we send up high power signals and actively disturb the space environment. We get radiation that comes back when we do that, and we do use sound. That's one way. We get various types of non-linear processes that impact the ionosphere, and we actually do use sound to try to get some idea of the physical processes that are going on. So we actually are, we do have people doing that, yeah.
Anything else? Well, thank you so much for listening.